Okay, in this last video we're going to look at some other examples of statistical graphs, and these are probably going to be fairly familiar here. So this first one is a pie chart, and this is a way of organizing qualitative data, and it's useful when you want to actually kind of show how much of the whole belongs to different categories. So oftentimes, like someone's budget or something, how much of your budget goes to housing, clothing, food, transportation, whatever. That's a very common situation where a pie chart would be useful. I chose this one because I thought it was kind of interesting. It's composition of the Earth's crust. So how much of the Earth's crust here are these different elements here. So it's kind of interesting that oxygen is the biggest element at 45.6%, and then a lot of silicone, some aluminum, iron, calcium, and then this other category here is one of the smaller categories. And so you can kind of compare then how much of the pie, goes to each category, and you can actually make these very accurate. If you have a protractor, if you remember those protractors from grade school where you could measure angles, what you can do is, if you know the percentage of the Earth's crust that's oxygen, then I can take 0.456 of 360 degrees, and the reason for that is the number of degrees around a circle is 360 degrees. 4 right angles, a right angle is 90 degrees, and 4 of those is 360 degrees. And so you take that percent of 360 degrees, and I get 164.16 degrees. And I might have I don't know if I have a protractor in there. I'm not gonna actually do it here, but you could actually lay your protractor on here and actually measure that angle so it's 164 degrees. And then these, that's gonna make the size of each piece accurate to what percent of the whole each category is, and you would get a nice visual representation. Okay, so another type of graph, it's called a time series graph, but normally we call these line graphs, and these are very common. You'll see them in newspaper articles and magazine articles. But the point here is you got a measure of time along the bottom. So in this case, these are years. And then you got the value of some variable along this axis here is graphing the value of some variable. And so what you're doing here is for each year, this is the number of airline departures. You're going to plot the number of airline departures for each year, and then you can connect them up, and now the line is kind of showing the trend in the data. You're seeing how that variable changes, how it increases and decreases over time. And I thought this was an interesting one because this is the number of airline departures, and you can see that it takes a dip in 2001, and you can probably guess why that is. That was with 9/11. It actually took a dip. There was a period of time they didn't even allow people to travel on the airlines, and then since then it's gone up. But this graph then allows you to change or see how a variable changes over time. The other neat thing is you can actually do more than one line. So I could have like a blue line and a red line, and maybe the blue line would be the amount of sales for Walmart, and the red line would be the amount of sales for Target, and you could kind of compare the two over time to see how they change and maybe even interact with one another. Okay, so those are called line graphs normally, or time series graphs, and they are very useful. Okay, now this next one, if you're going to be a teacher, take note here. This is going to be one of the most useful things you learn in this class. So if you're a teacher, especially if you're teaching like middle school, high school, or at a community college, you often want to know how the class did. You want to know the distribution of scores. And to make a group frequency distribution is pretty time consuming. You'd probably never sit down and make a group frequency distribution. But this graph is very, very easy. Basically, and it's perfect for seeing what the distribution of test scores are. Okay, that's the perfect use for this. And what you're going to do, these test scores go from the 20s to the 90s, and so I'm going to list the numbers 2 through 9 here, and these are representing the tens place. And they say that these are the stems, and then it's called a stem and leaf diagram. These are the stems, and these are the leaves, but these are the ones place. So what I do here for like 76, so I just do 2 through 10, and these represent my classes, and my classes just have a class width of 10. So this would be 20 through 29, 30 through 39, 40 through 49, so on. And so for 76, I put a 6 here for the ones place. 89, I would put a 9. 71, I would put a 1. 82, I would put a 2. And I just make sure these are all lined up really nicely. And then the length of each row kind of represents the bar in a histogram. You wouldn't even have to draw these bars, but you see you could turn this graph like this, and then you have your distribution, right? This is a left skewed, this would be a left skewed distribution of, and you can kind of see how the class did on their test. And this thing literally only takes like 30 seconds to make. You would just notice that you find the minimum one, 20s, 30s, whatever. You start with that, go down to 9, or you can even have 10 here if there's perfect scores, and then you just go through your data set and mark these in, and then voila, you have your frequency distribution. And so this doesn't work if you have really large data sets or ones that have a big range, so I couldn't have used this for the college tuitions. I mean, just think about it. It wouldn't work very well. But for test scores, for a class of anywhere from 30 to 50 students, this is the easiest, simplest way of seeing the distribution. Okay? And so finally, I just want to show you now an example of how someone could mislead people with statistics. So this came from a web page here that collected like actual examples of misleading statistics. And so they got these web pages out there where you can look this stuff up, and it's kind of interesting. But this came from a CNN, USA Today poll, Gallup poll, and it was in response to a judge's decision. And I don't know if you remember, but there was it was the Terry Schiavo case, and there was a lady who was in a coma. She had been in a coma for many years, had never woken up, and the husband wanted to take her off the feeding tube, but her family, her parents, did not want that, and so they went to court over this, and the judge actually favored the husband, in rule of the husband, and they took her off the feeding tube, and she died. And it was in the media a lot. It was very sad. But what this poll did is they contacted people, and they asked them, did you agree with the judge's decision? And obviously what this graph is wanting to show is that the Democrats overwhelmingly agreed with the decision, while the Republicans and Independents did not agree with the decision. So for whatever reason, they were wanting to show that the Democrats were much, much higher than the Republicans and the Independents. But this graph is misleading, and if you look real carefully, you can see why. This graph actually, it does not start at 0. This graph started at 53, and it went up to 63. Okay, so notice the Republicans and Independents both had a frequency of 54, and I think these are actually percentages. So 54 are the Republicans, 54 are the Independents, agreed with the decision. 64 or 62% of the Democrats agreed with the decision. So basically, since they started at 53 and they ended at 63, the Republicans and Independents just got to go up one notch on the graph, while the Democrats got to go almost to the top of the graph, and it made the difference seem huge, but it really wasn't all that big. So if you look at this graph here, if you go from 0 to 100, this is the actual difference between them. These are at 54, that's at 62. And so you can see that this is very, very misleading. And so what they actually did is they actually cut a little strip off here, right? And then they stretched that out over the whole graph to make the difference look much, much bigger than it really was. Okay? So that is misleading. And they're just assuming people are going to look at those bars and then just draw the conclusion that they want them to draw. Okay, as opposed to actually looking really carefully at what's going on. And the really interesting thing to me about this graph is they actually tell you what the sampling error is for this particular poll. And the sampling error here, it says it's plus or minus 7 percentage points. So what that means is when you do a poll, it's not going to accurately reflect what the true percentage is for the entire population. Okay, there's going to be some sampling error. So you would expect the poll to give you, if it was a fair poll and they actually took a random sample and there was a large number of people in the poll, you would expect these to be kind of representative, give you a good idea what the actual percentage would be, but there's going to be some error, and that's known as the sampling error. And in this case, it could be plus or minus 7 percentage points. So any one of these could be either 7 percentage points too small or 7 percentage points too large. So if you think about that, perhaps this 62% is 7 percentage points too large, and it should be down here. And the 54% maybe is 7% too small, and it could be up here, right? And so the actual values, these Republican independents perhaps are higher than the Democrats for all we know. And so what they would say is that the difference between these groups is not statistically significant. Or they would say there's not a statistically significant difference between the groups. And so if you wanted there to actually be a statistically significant difference between the groups, it would have to be that if you take the sampling error, and if you subtracted 7% from the Democrats and added 7% here, these would still be below these, right? So the difference is actually still there, even when you take into account that sampling error. If that's the case, then we would say that there's a statistically significant difference between the groups. But in this case, you don't even have that. So the interesting thing is, even though they made the graph misleading, they actually gave you the sampling error for the study, for the poll, and someone that understood how statistics works could actually look at this and know that there's not even a statistically significant difference between the groups. And so whether they put that there on purpose, whether they just figured that the majority of people that were looking at the graph wouldn't know how to interpret that, I'm not sure. But this is a really nice example where the best way to know how statistics is being misused is to know how it actually is used, and then you can apply it to whatever study that you're looking at to know if the results are reliable or not, or if there is a way. And sometimes you might not even know if it's reliable or not, but you know places where they could have been misleading, and you would actually have to go and get more information to know exactly how they conducted, like the sampling or whatever. But the only way you would know how to do all that, or even what to ask, would be to know how statistics is used. And so this is a nice example that shows that. So, okay. So in the next set of videos, for the next homework assignment, we're going to learn how to calculate the mean, median, mode, and the standard deviation.